Welcome at Ask the Professor. This is the last one of this course of track and train, and see that a lot of questions already discussed about tunnels and bridges. So a lot of questions are coming up. That's great. And also what we learned in this course is about what are the assets, what is the purpose, and what is the real combination to make a full system of it. And I think that's most important, how to see the assets not as an island but as a total system. A lot of questions came also about these assets, and therefore my colleague Jan Moraal will go and explain that in our lab in Delft, in university, not in this park. So he will go on with these questions, and I hope you learn that and you learn a lot about this system approach and why and how we do all these kind of testings in our lab. So good luck.
Hello everybody, welcome at TU Delft, and especially welcome in our railway laboratory. My name is Jan Moraal, I'm one of the technicians of our railway group, and today I will try to give answers to your questions for the Ask the Professor. Meanwhile, I would like to show you some of our interesting test facilities here. At this moment you see our famous V-Track scaled wheel-rail test machine running around. It's running at very low speed at the moment, but that's for my own safety, as you can understand. With this test machine we do a lot of research on the wheel-rail interaction, and at this moment we are running a test to investigate the friction between wheel and rail on different types of rail material.
Well, I hope you like these images as much as I do, but okay, let's go to work, let's go to your questions. Bernd and also Terence sent us a couple of pictures, and their question was, what do we see on these pictures, on these photos? Well, let's start with the first one. Let's see, maybe I should rotate it, then we can see it completely, yes. What we see here is typically a guardrail, and it's made, what I can see from here, it's made of a simple rail profile. This guardrail is used at places where if a derailment occurs, it is very important to keep the train on the track. For example, on bridges, in tunnels, you don't want a derailed train to hit a structure on the side of the track. What you see here from the position where the person who took the photo stood, you can see here on the left a concrete structure. And I think it's clear that this is a bridge over the track. So this guardrail is placed here to prevent the trains that derail to hit the bridge structure. And you can imagine that if the train derails, that the wheels will be guided in between the guardrail and this rail, and it cannot move any further in this direction. So I suppose here is a concrete pile. Why it's only on this side? Because I think on the other side of the track there is more space. So this structure, you see it everywhere, and it has a very important function. If you remember the train disaster in Germany near Eschede in, I think, almost 10 years ago, where a German ICE high-speed train derailed and hit a bridge and that bridge completely collapsed due to that collision. So very important structure, can be very simple, just simply one rail or two guardrails, one on both sides. One of the questions came from Bernd, and Bernd was interested in the transition zone. Here behind me we have a nice setup that we use for our practical courses and where students can build their own transition zone and it can be tested. This practical is called Bend and Brake, and well, the name already says a little bit about what it does. Students can build their own transition zone, find their own solutions, and we will test them. And then the question is, will they bend or will they brake? I will explain you in more detail how this setup works. Starting on the left side, we see our bridge construction. This is the red steel construction. And this construction can be adjusted in height. That's not the same as what will happen in practice, where the bridge will stay at the same level and the embankment will move in vertical direction. But here we do it the other way around, but the idea is the same. So this is the bridge construction. Then if we go to the right, then here you see the transition zone. It's a wooden box. In this case it's filled with gravel, but students can make their own construction. Not only use different sleepers, but they can also change the gravel and whatever is underneath it. Then finally we have the embankment. In this case just a steel construction. And of course this will not move, and only the left side, the bridge, can be moved in vertical direction. On the embankment we have the train, what we call our micro CTO train, named after our measurement vehicle that's named CTO. We use this train to load the whole construction. It looks small, but it has a total weight of more than 100 kilograms, so we can really cause damage to the structure. And of course you want to see the train running, well, let's do it. And of course we can go the other way around as well. Bernd's question is about the loading of sleepers by the wheel load. In our course and in our measurements and calculations, we assume that the wheel load will be distributed only in vertical direction to the sleeper and also in vertical direction to the ballast bed. But is that true? What Bernd says, if the load is passing the sleeper, it will first be on this side of the sleeper, and that could tend the sleeper to rotate in this direction. And after the wheel is passed, the sleeper could rotate in that direction. Due to that rotation, the sleeper could bury itself into the ballast bed. Is that true? Well, let's see. To answer this question, I made a small setup in the lab, and the setup consists of a single sleeper with one rail on a ballast bed. And now we can see that if the wheel load is passing from this direction into that direction, if I push here, the sleeper will rotate. And when the load is on this side, the sleeper will rotate as well in the opposite direction. So if this happens many times after each other, you can imagine that the sleeper will tend to bury itself into the ballast. So that's true. But in real life we have more than one sleeper, and what you can see here, if I put another sleeper not too far away, the sleeper will not rotate when I push on this side. So in theory what Bernd is saying is correct, but because of the stiffness of the rail and the distance between the sleepers, that's around half a meter, 60 centimeters up to maximum 1 meter, this rotation can be neglected, and also the effect of it on the deterioration of the ballast bed is much less than that of the wheel load. I hope this answered the questions. Another photo was sent to us by Terence. Terence is from Canada, and this photo shows a track construction, and we can see that the rail is fixed to the sleeper by 2 spikes, one on each side, or 4 spikes. Here we have 2 on this side and I think 2 on the other side. These spikes pass through a steel base plate, you can see them here and there, and that base plate ensures that the rail is positioned under correct inclination. There's a small angle, 1/20, 1/40, for correctly positioning the rail. Well, Terence was looking at this construction and he found, and he tried to highlight it, and I hope it is visible here, that you can simply see the spikes here, but beside it you can also see something that looks like a bigger spike or a clamp or whatever, and you see it here, and you see it there, and you see it also here and there. And if you look at the rail here, you see also that there is something like a clamp. Well, Terence wondered what these clamps or whatever this are about and what their function is. Well, before we can answer that question, it is important to know that the main function of the spike is to maintain the correct track gauge. And that means the distance between the 2 rails. And in all their simplicity, these spikes do their job very well. Because one single spike on this side and one on the other side of the rail can simply prevent the rail from sliding sideways. So with 2 spikes on both sides of this rail and on both sides of that rail, you can guarantee the correct track gauge. In the other directions, vertically and longitudinal, however, they can do very little to keep the rail in place. And this is in contrast to other mounting systems that use screws and spring clips. In the longitudinal direction, that means in the direction of travel, this can cause problems at locations where a lot of braking has to be done and where traction is given. We've seen that in the course, and we know in front of signals, at stations, platform tracks where trains stop and depart, and for example on slopes. In the recent weeks we have seen that huge traction and braking forces must be transmitted through the wheel-rail contact to the sleeper and on to the subgrade. Okay, and now back to the question. What are these things? What we see here are rail anchors, and these anchors are clamped around the foot of the rail on either side of the sleeper, and they simply prevent the rail from sliding in the longitudinal direction. So where do you find them in the real track? Well, you will find them in those places we mentioned earlier, near stations, on station tracks, in front of signals and on slopes. They come in different shapes and sizes, and luckily I have one in the lab here that we found in Sweden, so let's try to find it and then I can show you what it looks like. Okay, I found these anchors that we were talking about, and I made a small setup to show you the difference between the spiked construction and the more, especially in Europe, more standard construction. First of all, about these anchors. Well, as you can see from here, the anchors are very simple shaped pieces of steel, and they can be, by using a hammer or a special tool, you can put them around the foot of the rail, and you can imagine that if you hit this part with a hammer, it will slide in between this, and here you have a small piece where the foot will get in, and then it is clamped. Easy to mount and also easy to remove by hitting this side by a hammer. Here we see an anchor that is mounted on the foot of the rail, and of course we don't have a real sleeper underneath, but you can imagine that if we put one on this side and the other on that side, we can prevent the rail from moving. Okay, now you know what rail anchors are and what they do, and as long as the speed of the trains is limited, this type of track construction can function well. That is why spikes can still be found all over the world on freight railways with low speeds and not too intensive traffic. It is a cheap and easy to maintain construction, and of course replacing the many thousands of kilometers of spiked track is often not financially feasible. You will find a lot of them in North America, in Canada, and that's also why Terence, who's coming from Canada, could take this picture. Bernd sent us another picture, and this is a photo of a platform track somewhere in the Netherlands. I will see if I can rotate it. Yeah, that's better. What you see on the photo is something like a cable in the center line of the track. What we see here is a detection loop of the Dutch automatic train protection system called ATB, and more specific, it's the enhanced version of ATB. Well, I won't go into too much detail about this system, but it's interesting to know a little bit about this system. It uses beacons at fixed distances from a signal, and that starts with the first beacon at 120 meters, the second one at I think around 30 meters, and the last one is 3 meters in front of the signal. When the signal is a danger, the beacons will indicate the maximum allowed speed of the train at that position. And if the train moves too fast, the onboard system will intervene and the train will make an emergency stop. Well, this prevents the train from passing the danger signal. If the train has now stopped between two beacons, and that will almost always be the case at the station track, and if the signal turns to proceed, the onboard system will only receive this new information as soon as the next beacon is passed. And until then, the onboard system thinks that the signal is still in danger, and it will intervene as soon as the train starts running. Well, this detection loop, what we see here, makes it possible to provide the onboard system with the correct information so that the train can depart without intervention of the ATB system. And you will find these detection loops mainly at stations, on platform tracks, and in front of signals, over a length of about 120 meters, where the first beacon is positioned. So the next time that you're on a railway station in the Netherlands, just look around and see if you can recognize these beacons. And these beacons are rectangular yellow plates that are placed to the right side of the rail. You will easily see them, and then check if you can also see this cable of the detection loop. Okay, well, that's it for now. I hope I answered all your questions, and I also hope that you enjoyed the small tour through our laboratory. For now, I wish you all the best with your final assignment, and I hope to see you back in the B course, and maybe we will meet each other here sooner or later at TU Delft in our railway laboratory. Okay, we go back to Professor Dollevoet. Goodbye.
Hopefully you learned a lot about the video in the lab. You see a lot of ideas about the phantom brake, the transition zone and the rolling pantograph, and also different ways of how to make the track as a total, as a system. So I think that's it for this time. Hopefully good luck with your assessment. That's also important, and see you next time on the operations on the professional education. Keep on track.